Hello. Well, today we start properly the set about series solutions to ODEs. We've talked a little bit about power series and Taylor series in general, and this is what it was all for. Okay. So here's an example of a first order linear homogeneous ODE with non-constant coefficients. So the example is use power series to solve y prime minus 2xy equals 0. Okay, so I've underlined here power series and non-constant coefficients, right? We spent a lot of time talking about how to solve ODEs with constant coefficients, linear ODEs, homogeneous or not. And if we have non-constant coefficients, for first order, we've got that formula. But for second order and higher, we're really out of luck. We don't know how to solve linear ODEs with non-constant coefficients of second order and higher exactly. So these power series solutions are very powerful. All right. I also wanted to say that this is a little bit of a help with problem 2. It's like problem 2, sort of. Okay. So here's where we start. We start by writing our solution y of x as a power series in x. And we're almost going to always use a Maclaurin series centered at 0. So y is sum from m equals 0 to infinity cm x to the m. And you notice I wrote m, not n. And I want to point out that I could have written, and usually I would write, and the book would write, n equals 0 to infinity cn x to the n. And these are actually the same. The m here and the n here are what we call dummy variables. Because if I write it out from either formula, I get c0 plus c1x plus c2x squared plus dot, 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 right? What it actually boils down to when I do the sum doesn't have an m or an n in it. Okay, and we'll see why it's kind of useful to start with the m. All right, so we want to differentiate. Now, we love to differentiate polynomials. And differentiating a power series is just like differentiating a polynomial. Okay, now, you notice that that was y. Here is y prime is going to be c1 plus 2c2x plus 3c3x squared plus dot, dot, dot. Actually, when I do this sum, it's not m equals 0, it's m equals 1 to infinity. I mean, you could, in a way, include the m equals 0 term because it just has this m equals 0 as a factor here. But if m equals 0, this is x to the minus 1, and it's a little bit of a problem, so it really shouldn't be there. And you notice here, y prime just starts with the c1 term, right? So let's plug this into the ODE. So we get, when I plug into the ODE, I get y prime sum from m equals 1 to infinity cm times m times x to the m minus 1 minus twice times x times sum m equals 0 to infinity cm x to the m, right? And that has got to be 0. All right, now this thing here, I can replace the x times that with an m plus 1. Right? Okay. So, right, multiplying this whole power series by x just increases the exponent. Okay. So now the key here is I want to write this as a single power series with a sum of something times x to the same power, right? This has the x to the m minus 1. This has x to the m plus 1. Let's make it the same power. And this is kind of why I started with the m. For this term, I'm going to let m minus 1 be n. So I'm going to call that x to the n. And over here, I'm going to let m plus 1 be n. So these both turn into something times x to the n, okay? And let's think about this. I can solve for what m is, right? M is n plus 1 here, and m is n minus 1 here. And I also want to start thinking about the first term. Here, m equals 1. That corresponds to, when m is 1, n is n minus 1. Here is n equals 0, right? When m is 1, n is 0. When n is 0, m is 1, right? So here we have the first term is m equals 0. In m equals 0, that corresponds to n equals, well, m plus 1, that's 1. All right? So let's get rid of all of this stuff. All right. So now let's rewrite this sum, rewrite the differential equation. We get sum from, there was m equals 1, but that's now n equals 0. N equals 0 to infinity. C sub m, but m is n plus 1. And then m is n plus 1. And now it's the payoff, it's x to the n, right? And then minus twice sum, okay, m equals 0 corresponds to n equals 1. And then I have c, so in this case, m is n minus 1. And then again, the payoff is that this is x to the n. Okay? All right. So I have all the powers of x the same, but I want to combine these terms. And you notice I can't combine the n equals 0 here because there's no n equals 0 here. So I've got to write the n equals 0 term separately. And when n equals 0, I get c1 times 1 times x to the 0, which is just c1. Oh, I'll write it to see where it comes from. But now I can do a sum from n equals 1 to infinity, right? So I took this and I kept the n equals 0 separate, and then I have the sum from n equals 1 to infinity all there. And now I can combine the two terms. So what do I get here? For this term, I've got cn plus 1 times n plus 1. And then I'm going to factor out the x to the n. And then over here, I have a minus 2cn minus 1. All that times x to the n. And that should be 0. Right? That should be 0. But this is, remember, the 0 function. So that's really equal to 0 plus 0 times x plus 0 times x squared plus 0 times x cubed. Need I say more, right? the coefficient in front of x to every power on the right-hand side is 0. So we need to have the coefficient in front of x to every power being 0 on the left-hand side. Cool. All right. So this thing, first thing we have is C1 has got to be 0. And then the thing inside the square brackets has got to be 0. Cn plus 1 times n plus 1 minus twice Cn minus 1 equals 0. And that's for n equal to 1, 2, 3, 4, etc. Right? So then what we typically do is we solve this for the highest subscript. And let's not forget this. So we have C1 equals 0 and Cn plus 1, bringing that over, gives me a 2 Cn minus 1 divided by n plus 1. Okay, oops, and I really should be specific for n equals 1, 2, 3, dot, dot, dot. All right, so this thing here is what we call the recurrence relation. The recurrence relation is sort of the halfway step. It's okay. Okay, you can send me an email if you think the microwave is too loud. All right, so this is sort of the halfway step to problems like this. You have a differential equation, you plug in the series solution, and this has the coefficient Cn in it, and then you get a recurrence relation for those coefficients. And often, like this case, it has something at the beginning that holds for one or two steps at the beginning, and then from then on we have a formula with an n in it. All right. So now the second step is to solve the recurrence relation. So the first step is to plug in the series solution and get a recurrence relation. Second step, I'll even write that out. This happens in all sorts of series solutions. Step 1, you plug in y equals sum from n equals 0 to infinity Cn x to the n and get a recurrence relation. For the coefficient Cn, right? Okay, and then the second step, which we're about to start, is to, quote, solve the recurrence relation. In other words, get an explicit formula for Cn. See, this is not an explicit formula for Cn. This is just like a rule of how to figure out what Cn is. Okay. Well, let's do it. All right. First, we got C1 is 0. Okay. And then when I plug in n equals 1, I get what C2 is. C2, when n is 1, is 2 over 1 plus 1, which is 2, times C1 minus 1, that's C0. That's just C0. Right? Cool. Okay. Now what is C3? C3, when n equals 2, is going to be 2 over 2 plus 1, 2 over 3 times C1. Oh, but C1 is 0, so this is 0. Okay, so what happens when n is 3? I get, when n is 3, I get what C4 is. C4 is 2 over 2 plus, or no, 3 plus 1, 2 over 4 times C, again, n is 3, 3 minus 1 is 2, C2, okay? So this is equal to a half from that term, but C2 we already knew, C2 is C0, okay? And then we could do n is 4, we get C5, and then n is 4, C5 is 2 over 5 times C3. Oh, but C3 was 0. So this is equal to 0 too, as well. And then we have n equals 5, we get C6. Now we've, one of the things that often happens, you notice, I don't have to, you notice that that number is the same, so it's going to be 2 over 6. Right? And then I have C4. Oh, but what's C4? C4 is a half C0. So this becomes a third, 2 over 6 is 1 over 3, times a half C0. So this is equal to C0 over, let's write it as, I don't know, 3 times 2. I could write it as 2 times 3. But, okay. So let's see if we can figure out what happens. Well, notice that C1 is 0, C3 is 0, C5 is 0, and C7 is going to be 0, right? All of the Cn's, if n is odd, are 0. So I'm not going to call it Cn, I'm going to call it C2n plus 1, right? So we have, the result is C2n plus 1 is 0 for integers n, right? And integers starting with n equals 0, right? And then what about the odd n's? Well, for odd, let's just recall we have C0 is anything. C0 is anything, and that's kind of an important thing. This recurrence relation says nothing about C0, okay? C0 is arbitrary, could be anything. Could be 0, could be 7, could be minus 5, could be just C0, an arbitrary constant. And then we got C2. C2 is C0 as well, okay? I'm going to erase that. Let's remember that we got C6 is C0 over 3 times 2. What did we get? We got that C4 is C0 over 2. C6 is C0 over 3 times 2. And what do you think C8 is going to be? C8 is going to be C0 over 4 times 3 times 2, right? You can do it. And C10 is C0 over 5 times 4 times 3 times 2. All right. So let's see if we can summarize this. To solve this recurrence relation, we found that C2n plus 1 equals 0. And I think you can see it. C2n is C0 over n factorial. And this is for n equals 0, 1, 2, 3, ... Right? Now, sometimes we can get a closed formula for all the CNs like this. Sometimes we can't. But this is really beautifully solved. When we say solve the recurrence relation, we don't always need to get a formula for C, any of the constants C. It's nice if we can. Sometimes we just find C0, C1, C2, C3, C4, C5, and we're done with it, okay? All right, so I think I can erase everything, but you see how this happens. All right, so finally we can get our solution. So the solution to the ODE, which is y prime minus 2xy equals 0, is, right? Y is some, okay. Well, it was n equals 0 to infinity cn x to the n, but now all of the odd subscripts for c are 0, and the even ones have this formula. So instead of writing it like that, I'm going to write it as y is sum from n equals 0 to infinity. And I'm going to put in x to the 2n. And then we have c0 over n factorial. All right? So this is actually c0 times sum from n is 0 to infinity x to the 2n over n factorial. Okay? That is the general solution. All right. So, cool. And you notice that the general solution is a constant, an arbitrary constant times a given function. In fact, that's exactly what we would have done back in the original day, right? So, since this y prime minus 2x y equals 0 is linear, in fact, it's also separable. I would probably do it as a separable equation. I can write dy over y is, let's just go through that a little quickly. A little hint. If I write this out, I would get dy over y is 2x dx, and I integrate natural log of absolute value of y is x squared plus a constant. So y is e to the, absolute value of y is e to the x squared plus c, or y is plus or minus e to the c times e to the x squared. So I call this whole thing C0. Okay, so here is the general solution, which we could get for a lot less work than the power series, but we can also compare it. You notice the known solution, y is C0 e to the x squared, has the power series. What is the power series? Well, we know the power series for e to the anything. It's 1 plus a thing squared over 2 plus, right? It's 1. E to the x squared is 1 plus x squared plus x squared squared over 2. And I can put a factorial if I want, plus x squared cubed over 3 factorial plus x squared to the 4th over 4 factorial plus dot, dot, dot. And you notice that's exactly what we said there, realizing that x to the 2n is also x squared to the n, right? So we've reproduced this known solution. Okay, so, all right, so this, as I said, this is a technique that you can use in second order ODEs, and in the homework, we're mostly going to be doing it for second order, but the first order examples kind of illustrates how it works. And like problem 2 in the web work, It often happens that what you get for the recurrence relation is you get one or two terms to start the things off, or maybe even three to start things off, and then you get a formula for Cn plus 1 or maybe Cn plus 2 in terms of the earlier Cn's. And so you can just kind of go one by one. Um, you can start finding out what all the Cn's are. Now, sometimes you can find a pattern, sometimes you can't. And to be honest, usually you can't find a pattern, because if you could find a pattern for the Cn's, probably there's an exact solution there somewhere that you just failed to find. And our real purpose for doing these series solutions is to find new solutions that we can't find by the other techniques we've already learned. Okay, all right. So stay well and keep working, and let me know anytime you have troubles. If things are going on, you can always contact me. All right, send me email, send me a text, phone me up if you want. I've given you my cell phone, not on YouTube, but if you're my student, I sent you my phone number. All right,